Hello everyone, this is Professor Ng Chi Kun from Minimas. In this video, I'm going to give you a tutorial solution on inference lines for statically determinate structures, which is a beam. Okay, so the question is to construct the inference line for the shear force at C of the beam. So point C is a point, it is 3 meters away from support A, and the beam is a simply supported beam with 10 meters span. Okay, so we are going to study what is the inference line for the shear force at point C here. So following the lecture, we have two methods of drawing the inference line. The first method is by tabulating values. Okay, so we tabulate values of the shear force for 1 unit force that is placed at different points of the beam. Okay, and then the second method is to write the equations for the inference lines. Okay, so first of all, we want to use the method of tabulating values. Okay, so to tabulate the values, we have to select points on the beams. Okay, so we start with x equals to 0, which is the support A, and then we select 1 meter away from support A, and then 3 meters away from the support A. So these 3 meters here is a very important point here, because this is a point where we look at the shear force. And then we select another 3 points at 5 meters, 8 meters, and 10 meters. Okay, so let's look at the first point here, right? So the first point is where x equals to 0. So x equals to 0, meaning that the 1 unit force is exactly at the support A here. Okay, and then C is here, 3 meters away from support A. So once the 1 meter force is at support A there, okay, then if you determine the direction, this direction is 1. Okay, and then this direction is 0, right? And then if you want to calculate what is the shear force at C here, so remember that for bending moments and shear force, we are using the positive sign convention. Okay, so for positive shear force sign convention, we are using a deformed shape of an element like this. Okay, so in this case, the shear force on the left hand side of the element is upward, and the shear force on the right hand side of the element is downward. Okay, so this is the positive sign convention that we use to draw either shear force diagram or inference line for shear. Okay, so we know that this is 3 meter. Point C is at 3 meter away from point A, and then this force is 1 unit, and this reaction is also 1 unit. And then the shear force at point C, we use the positive direction, okay, where the shear force on the element is on the right hand side of the element. So this is a positive shear force, right? So this is VC. So if you calculate VC here, you see that this is 1 unit. Okay, so 1 unit here, 1 unit here. So if we sum all the forces in the vertical direction and take upward force as positive, so we have 1. We have 1 here, and then minus 1 here, and then minus VC equals to 0. So in that case, we get VC equals to 0 in this case. Okay, so meaning that when x is equals to 0, VC equals to 0. So here we have 0 for VC. Okay, so next we look at another case where x is equals to 1. Okay, so this is 1 unit force, and then this is 1 meter, because we have selected x equals to 1 meter. Okay, so and then this is C here, which is 3 meters away. Alright, so in this case, okay, if you solve for the reactions, okay, so direction here will be equals to 9 over 10, and direction here is equals to 1 over 10. Okay, to get this direction here, you can sum moment at B. Okay, you can sum moment at joint B here. Alright, so you get this force, okay, this force times 10 meter should be equals to this force times 9 meter. Okay, so this force is 9 over 10. Alright, so in this case, if you get the shear force at C here, BC, which is 3 meter away, right, and then this reaction is 9 over 10, and then don't forget that we have 1 unit force here, which is at 1 meter away from point A. So in this case, if you use equilibrium to calculate for shear force VC, okay, we'll get VC is equals to 9 over 10 minus 1. Okay, so that gives us VC equals to minus 1 over 10. Okay, or minus 0.1. Alright, so here we have VC equals to minus 1 over 10. Alright, so we can plot VC equals to minus 1 over 10, probably over here. Okay, the point is somewhere here. Alright, and then next we move on to 3 meters. Okay, so when x equals to 3 meter, right, so now x is exactly at point C there, so you have to be careful here, okay, because now we have two shear forces at point C for this condition. Okay, so one condition is that the unit load is on the left hand side of point C. Okay, and then the other position for the shear force at point C is when the one unit force is just to the right of point C. Okay, so there are two conditions here. Alright, so first we look at the situation when the one unit force is on the left hand side of point C. Yeah? Okay, so in this case, this is 3 meters away. Okay, the whole beam length is 10 meters. So in this case, we're going to get 7 over 10 here and 3 over 10 here as the reactions. Okay, so now we want to see what is the shear force at point C there. Okay, so the 1 unit force is still here, because when we cut across section C, because this force is still on the left hand side of joint C, so this force is still appearing in the free body diagram. And then this is 7/10, and then this distance is 3 meter. And then we draw VC in the positive shear force direction. Right, so this is 1 unit force. Okay, so you want to solve for VC here. Okay, so we get VC is equals to 7/10 minus 1. So that gives you VC equals to minus 3/10. Right? So we have minus 3/10. Okay, so as I mentioned just now, for x equals to 3 meter, there are two positions that is possible for the 1 unit force. Okay, so the second situation is that the 1 unit force has already moved to the right of joint C, but it's still at 3 meters. Okay, probably we can call that the 3.00000001 meter. Okay, which is 3 meters. Okay, and then just now here we can say that this force is at 2.9999999 meter. Okay, before reaching joint C. Right? So in this case, this reaction is still the same, 7/10, because this is still 3 meter. This is still 1 unit force. Okay, we still have a reaction of 3/10 here. But now if we cut across joint C, okay, you will never see this 1 unit force anymore, because the 1 unit force doesn't appear in the free body diagram anymore. So this is 7/10. This is 3 meter. Okay, so we have shear force BC. So in this case, shear force BC here is equals to 7/10. Alright, so now when x equals to 3 meters, we have two shear force values in the inference line. Okay, so meaning that we have 7/10. Okay, so just now we have at 3 meters here, we have minus 3/10, so minus 3/10 is somewhere over here. Okay, so in this case, we can plot this line here, which is a straight line. Okay, and then at 3 meters here also, we have also another shear force value, which is 7/10. So 7/10 is somewhere over here. Okay, so there's a jump in shear force at this 3 meter location. Okay, because one value is when the 1 unit force is just to the left of point C, and then another value is when the 1 unit force is just to the right of point C. So the value for the shear force just to the left of point C is this value here. Okay, minus 3/10. Okay, and then the value just to the right of point C is this value here, which is 7/10. Alright, So next we still have 5 meters, 8 meters and 10 meters. So we move on. Okay, so when x equals to 5 meters, okay, so this is the 1 unit force is exactly in the middle of the beam. Okay, so this is symmetrical, so meaning that this reaction is 1 over 2. This reaction is also 1 over 2. Okay, so now we are still interested in the shear force at joint C. So you just cut across joint C here, put in the shear force DC. Strictly speaking, there is still bending moment at the cut section. Okay, but we're not interested in the bending moment, so we don't need to put in the bending moment MC there. If you're interested in MC, please refer back to the video lecture, okay, when we are calculating bending moment for one point in the middle of the beam, MC. Okay, but the point C in the example is different location from this example, so please take note. Right, so the direction here we know that is 1 over 2. Okay, and this is 3 meters away. So in this case we have V C equals to 1 over 2. Alright, so when VC equals to 1 over 2, then at x equals to 5 meter, we have VC equals to 1 over 2. Okay, so 1 over 2 is somewhere here. Okay, when at x equals to 5. And then when x equals to 8 meter, so the 1 unit force is at 8 meter away. So this is 5 meters. Don't forget to put in. Right? So this is at 8 meters away. So in this case, if you solve for the support reaction, okay, so this will be 2 over 10, this will be 8 over 10. Okay, so joint C is, point C is there. Okay, so if you draw a free body diagram for a cut section at point C here is 3 meters away. Alright, and then we have BC here. Okay, so this is 2 over 10. So in this case, when we solve for VC, then we get VC equals to 2 over 10. So this will be 2 over 10 or 1 over 5. Okay, so this is somewhere here. Alright, and then when x equals to 10, when x is equals to 10 meter, okay, we have a beam where the 1 unit force is at the support B. Okay, so in this case the support reaction is 0, the support reaction is 1. And point C here is at 3 meters away. Okay, so if we cut across section C and then isolate as a free body diagram, okay, so this is 0, this is 3 meters. So in this case VC equals to 0. Okay, so in this case VC equals to 0, so we have 0 here. Okay, so if you join these points here, then we are going to get straight lines like this. Okay, so in this case I'm using freehand to draw it. So this one you get a straight line. So this is the shear force inference line for point C, okay, VC. So now we have already solved for the inference line for joint C using the tabulated values, right? So next we move on to the writing the inference line equation. Okay, so to write inference line equation, we don't set values for x. Okay, so we just set x to become a variable. So in this case, we have to determine the reactions in terms of x. So we have already done this in the lecture. So this is x, right? This is 1 unit force. And then the span of the beam is 10 meter. Okay. So now our point C is 3 meters away. Okay. So the inference line for 0 to 3 meter and from 3 meter to 10 meters, they are of different function or different equations. Okay, so we have to get our shear force equation for x greater than 0 but when it's smaller than 3 meter. Okay, another condition is that when x is greater than 3 meter and then smaller than 10 meter. Okay, so meaning that we have two functions here. Okay, or two equations. Right? So in this case, we need the reactions. Okay, so to get the reaction of VA there, okay, we can sum moment at joint B. Okay, so in this case, we get VA times 10. Okay, and then we minus 1, which is the 1 unit force, and then the moment arm is 10 minus x, and then this will be equals to 0 if we sum moment at joint B here and take clockwise moment as positive. Okay, so this is by summing moment at B by taking clockwise moment as positive. Right? So in this case, we get VA is equals to 10 minus x over 10, isn't it? Okay, so equals to 1 minus x over 10. Right? And then there is only one equation for the reactions VA. Okay, so in this case, we can write the two equations, okay, for 0 to 3 meter and from 3 meter to 10 meter. So first we write the equations for x equals to 0 to 3 meter. Okay, so in this case, meaning that x is less than 3 meters. Okay, so meaning that point C is here. Okay, now we have VA here, which is equals to 1 minus x over 10. Okay, so meaning that when x is less than 3 and more than 0, meaning that the 1 unit force is within AC, right? So this is joint A, this is joint B. Okay, so the 1 unit force is there, right? Where this is 3 meter. So in this case, if we cut across joint C there, so we know that this is VA equals to 1 minus x over 10, right? So the 1 unit force is here, so this is x, Okay, so this is joint C, so we have VC there. Okay, so in this case, we're going to get VC, okay, this is 1 unit force there. So in this case, okay, if you sum all the forces in this free body diagram, okay, and then we're going to get VA minus 1 minus VC equals to 0. So meaning that 1 minus x over 10 minus 1 minus VC equals to 0. Okay, so in this case, VC equals to minus x over 10, isn't it? So from here, we get VC equals to minus x over 10. Okay, so VC equals to minus x over 10 is actually the function of this line here. Okay, this is minus x over 10. Okay, so you see, this is x equals to 1, so this is 1 over 10, right, over here, that we have solved. Okay, this point here, okay, this point here is at 3 meter. When x equals to 3 meter, then 3 over 10 minus, right, so minus 3 over 10, right? So we can only use this equation from 0 to 3 meter. Okay, so remember that. Okay, we can only use this equation from 0 to 3 meters. And then more than 3 meters, we haven't written the equation yet. So let's look at when x is equals to more than 3 or less than 10. Okay, so in this case, C is there. We know that this support reaction VA is equals to 1 minus x over 10. Okay, and then now the 1 unit force is at the location where it's beyond point C. So this is x. Okay, so when you cut across section C here, and then this is the shear force C, and then this is the reaction VA, which is equals to 1 minus x over 10. Okay, and there is no other external forces because this 1 unit force is already on the other side of the free body diagram. So in this case, if we sum all the forces in the vertical direction and take vertical direction as positive, so we have VA minus VC equals to 0. So we have 1 minus x over 10 minus VC equals to 0. Okay, so we have VC equals to 1 minus x over 10. Okay, so this is another equation for when x is more than 3 meter and then when x is less than 10 meters. So the equation that we have just written is actually the function of this line here, which is equals to 1 minus x over 10. Okay, so when x is equals to 5, then 1 minus 5 over 10 is 1 minus half, so it's half. Okay, same as the tabulated value. And then when x is equals to 8 meters, so 1 minus 8 over 10 is 1 minus 4 over 5, so it's 1 over 5. And then when x is equals to 10, then 1 minus 10 over 10 is equals to 0. So this is for the shear force at point C when x is more than 3 meter and is still within 10 meters. Alright, and then the equation written previously, this is for the shear force at point C when x is equals to 0 and less than 3 meter. So in this tutorial, I've already shown you two methods of plotting the influence line for shear at a particular point in the simply supported beam. Thank you very much for watching.